getting into proofs today. Yes, I understand it's not your favorite thing in the world to do. But it's okay. We'll survive. Oh, well, that was like a domino effect. Okay, so the goal for today is that we want to show that a quadrilateral is a parallelogram. Well, back in section 8.2, again, we said that the definition of a parallelogram is that it's a quadrilateral of two sets of opposite parallel sides. And because of that, we know opposite sides are congruent, opposite angles are congruent, consecutive angles are supplementary, and diagonals bisect each other. So if I wanted to prove that a shape is a parallelogram, I should show these things. Okay, so our first justification that we can use to prove that a quadrilateral is a parallelogram is to show both pairs of opposite sides are parallel. So if I can show that both pairs of opposite sides are parallel, then I can say, yeah, that quadrilateral's a parallelogram, right? And that's just based off of our definition. So now let's think back to chapter 3. How did we prove that lines were parallel? Because we did do proofs of proving that lines are parallel. Well, let's think in reverse. Let's do the converse. If parallel, then alternate interior angles are congruent. So if I can say if alternate interior angles are congruent, then can I then say my lines are parallel? Yeah. Okay. So that's one way that we can prove that lines are going to be parallel to each other in a two-column proof format. We'll do it separately in a coordinate plate proof. Think back to chapter 3. When we graphed parallel lines, what was true about the slopes of parallel lines? What should be true about the slopes of parallel lines? Wouldn't they be the same? Right? Remember finding slopes of lines way back when? Okay, so that's option number 1. Option number 2. Show both pairs of opposite sides are congruent. Now this is Theorem 8.7. You do not need to memorize these numbers, so I wouldn't even worry about writing that down. I just was being lazy and screenshot it from the textbook pages. So show both pairs of opposite sides are congruent. So let's think about how we get congruent sides. Well, we get congruent sides from congruent triangles. We get congruent sides by finding the length of the actual side. And we find the length of actual sides using the distance formula. Do you guys remember the distance formula? That big square root one?
Yeah.
Square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 was squared. Maybe, kind of. We'll get there when we get to our coordinate proofs. All right, number 3. We can show both pairs of opposite angles are congruent. So show both pairs of opposite angles are congruent. Okay. So again, we can get opposite angles being shown congruent by getting congruent angles in congruent triangles. A little bit hard to do on a coordinate plane in our coordinate proofs to show congruent angles, so we probably won't be using this one as much. Now, number 4, here we talked about consecutive angles being supplementary. That one doesn't quite work as nicely in the proof world because in order to show supplementary angles, you need actual values for your angles to show they add up to 180. So that's never really used in the proof world. So there's a new one we're going to add in here, which kind of puts together line 1 and line 2. So if I focus just on one set of opposite sides, so if I can show that one pair of opposite sides are congruent and parallel, then I can say it's a parallelogram. Take notice, it needs to be the same set of opposite sides. I can't have one set of opposite sides congruent and then the other set of sides parallel. It needs to be the same side. It needs to be showing both congruency and parallel. And remember, there are those triangles being parallel. Remember that, right? Forgot to mention that back when we wrote number 1. All right, and then the 5th one gets us to our diagonals. Any guesses what I was going to say? Show diagonals bisect. Good. All right, so number 5. Oops, come back. Hit too many times. Show the diagonals bisect each other. Remember, bisect means it cuts it in half. So show the diagonals bisect each other. Okay, so we're going to do a 2-column proof on the front. Practice tiny writing, because I think we've got about 7 lines we got to do.
Is each other one word?
Huh?
Is each other one word?
No.
Each other?
Each. It's a word, other is a word.
Each other.
Okay, are we ready?
Each other.
Maybe I just think like each other. Are you making a T chart?
T-chart.
Oh, column.
Just waiting for everybody. Okay, here we go. 2-column proofs.
When you say 2 columns,
No, there's not a proof of 4 columns. Only 2 columns. All right, statements on the left. Reasons on the right. Line 1 is always our given. If you want to be lazy and just put a big fat given across, feel free to do that, but I'm going to write it out. So we've got line segment QR is parallel to PS, and QR is congruent to PS. So we are proving why theorem, what was that? That was the 3rd one that we had there? No, 4th one. So we're proving why the 4th theorem that we wrote up in our list works. So we're doing the proof of that theorem. So in order to do the proof of this theorem, my end goal is going to say something to the effect of, if opposite sides are parallel, then it's a parallelogram, because that is my definition of a parallelogram. So I need to, somewhere in my statements, show 2 sets of parallel sides. Well, the nice thing is I already have 1 in the given, so now I need to get the 2nd set of parallel sides. So in order to prove these theorems, we need to get 2 sets of parallel sides. Okay, so what's our rule of thumb with proofs? What's the first thing we're looking for?
Vocabulary.
Vocabulary, in this case, it's the symbol, which means parallel. So if parallel, then what? If parallel, then we get alt int angles congruent. Good. Okay, so we just concluded that I have alternate interior angles congruent. So that means on the other side, I need to show my alternate interior angles being congruent. So it's going to be angle something is congruent to angle something. So where are the alternate interior angles? I'm going to put numbers here. You don't do that. I just want to see if you can recognize them. Which set am I going to use? 1 and 4 or 2 and 3? I'm going to use 2 and 3. Why not 1 and 4?
because you don't know that Q and P and that's our...
Yeah, we don't have our parallel lines over here, right? So we eventually want to get to these lines being parallel. So we eventually want to get to 1 and 4 being congruent to each other, and we'll slowly get ourselves there. Okay, so 2 and 3 are our alternate interior because those are the ones that are working off of my parallel lines. So let's name them. So angle RQS.
I have a question.
Yes.
couldn't you just do number 4 and prove it? Really?
No, because I don't have parallel lines here, so I don't know. This could be wider than 1 because they don't have parallel.
Parallel lines and 1 pair congruent.
Yes, but my congruent ones are 2 and 3 because those are the ones that work off of the side that is parallel. I need to get to 1 and 4 being congruent so I can then say that those sides are parallel. Okay, so 2 is RQS, 3 will say PSQ, so angle PSQ. Okay, ran out of vocabulary, so then what's the next thing we go to? No, we're all done there. Adam?
Oh, never mind. I was gonna say, that the corresponding angles would.
Yeah, we don't have corresponding in this case. Yeah, because corresponding would be like the triangle with the line in it. If we run out of vocabulary, then our next go-to is either reflexive property or vertical angles. Which is it in this case? No bow tie up there. So the reflexive property is the diagonal. So QS is congruent to SQ because of the reflexive property. So now we have a side congruent to a side. We did an angle congruent to angle, and now we just did a second side congruent to itself. So which theorem tells me that this triangle is congruent to that triangle? Side, angle, side. All right, so let's do that. So line 4. Yeah, oh, we're going there. You guys, you're getting excited. I see it. So triangle QPS is congruent to triangle SRQ because of side angle side congruency. So now that I've got congruent triangles, I can say that any part of these triangles will be congruent to each other. So we are going to do a CP-CTC, but we got to pick the correct corresponding part. Well, let's think about this. My end game needs to be that I have a second set of parallel lines. Well, what must be true in order to get these lines to be parallel? Which angles need to be congruent? 1 and 4, those alternate interior angles. So my line 6 is going to be if alt int, I told you to write tiny, angles congruent, then parallel. I warned you, 7 lines.
I got a lot of space.
So here, oh, hold on. Oh yeah, okay, I didn't put my 5 over here. I was confused for a second. So over here, 5, I didn't do my 5 over here. We did a CP-CTC. So now I need to pick out the corresponding part of congruent triangles that I'm choosing to show congruent. So that was 1 and 4. So naming angle 1 is PQS. So angle PQS is congruent to naming angle 4 would be RSQ. So because these are alternate interior angles that are congruent, then my lines must be parallel. So over here in line 6 on the left, I need to name those lines that are parallel, which would be QP, bless you, is parallel to SR. So now do I have 2 sets of parallel lines on my left side? I do. I had it up there at line 1, and it took a long time to get to the second one, all the way down at line 6. So now can I say PQRS is a parallelogram? Yes. Okay, so line 7, rewrite your proof. PQRS is a, and if you want to use the symbol for parallelogram, it's just parallelogram. Can you give me an if-then statement for down there? Bless you. If what, then what?
Is it 4 now?
Well, so what should be my if-then statement?
If,
What we were showing what over here? I needed
areas
to.
of this size are congruent and parallel, then
Nope.
parallelogram.
Nope, that's what we started with. In order to show it's a parallelogram, we needed what over here? We needed two sets of parallel sides. So if opposite sides parallel, then parallelogram. Right? So that's our definition of a parallelogram. Okay? So when you're doing all these proofs on these theorems, your goal is to somewhere get two pairs of opposite sides parallel. Well, luckily we had one in the given, and then I had to do some work to get the second one. Okay? Do we mostly follow that?
I'm not doing coordinate proofs.
All right, coordinate proofs. We're going to do one coordinate proof 3 different ways. The beauty about coordinate proofs, Aiden, put your phone away, is that you get to choose the method that you like the best. On your quiz and on your test, I am not going to say, prove it this method. So you pick the method that you like best and use that. Okay, so some are easier than the other ones. So for me, I probably use the easier one than the harder one, but that's up to you. You do you. If you like to challenge yourself, then do the harder ones. Okay, so a coordinate proof is when you put an object on a coordinate plane. And a coordinate plane is just your XY axis with your 4 quadrants all the way around. And then you use coordinate geometry to show that things are happening. So here they already plotted the quadrilateral for us. Would you guys be able to plot these points if necessary? Okay, good. So we all know how to plot points. Perfect. Okay, so the first method that we're going to do is using our definition, which is showing that opposite sides are parallel. So method 1, oops, I'm in highlighter mode. Show opposite sides parallel. And what did we say about lines that are parallel? The slopes should be the same, right? So I'm going to put a little parenthesis here. We're looking for the same slope. So if I can show that the sides opposite from each other have the same slope, then I can say that the lines are parallel, which then means it's a parallelogram. Do you remember how to find slope?
Like
Yeah.
Nope. That's slope-intercept form.
Rise over.
Rise over run, right? Change of y over change of x, which if it's already plotted there for you, just do your rise over your run. Okay, so let's just do it.
If it's not on an exact point, what would we have to do the distance formula?
They should always be on an exact point. Yeah. All right, so let's find the slope. I'm going to do a little subscript here of line segment AB just to keep myself organized. What is the slope of line segment AB on the left?
4.
Is it positive or negative, first off?
Negative.
Negative. It's going down how many? 4. So does everybody see how it's going down 4 over 1? You just count them. So all you're doing is you're going down 1, 2, 3, 4, running 1. So negative 4 over 1, which is 4. Okay, so now let's go to the side opposite of that, which is CD. Is it also going down negative 4, running 1? It is. So those slopes are the same, which means that AB is parallel to CD. So I checked half the box. Now I've got to do it to the other set of opposite sides. So let's go up top here. I need to find the slope of line segment BC. Well, from B to C, we're rising, looks like 2. Going up 2 over 1, 2, 3, 4, 5. So the slope would be 2/5. I'm not doing anything crazy here, am I? We're all okay? Is that the same for AD? Yes. So are those lines parallel?
Yeah.
So then I'm going to write BC, line segment BC is parallel to line segment AD. So are both sets of opposite sides parallel?
Yeah.
Yes. So then I would do something like if opposite sides parallel, then parallelogram. Done. That's probably the easiest thing to do because it's pretty easy to just count rise and runs. Would you agree?
On any test or quiz, is it going to be more complicated, or should we be able to just count it?
Yeah, I mean, the only thing that might be a little bit harder is you might have to plot the points yourself.
Oh.
Like, I might be lazy and not give you the actual shape in the grid. You might have to put your shape in the grid.
There's too many extra steps.
I think you guys can handle doing that. All right, method number, we're going to work our way from easiest to hardest. Does that sound good?
Well, we should just stick with the easy.
Well, maybe someone would prefer this method better.
Right now and then go to the
Method number 2. I'm going to go to my diagonals bisecting. So show diagonals bisect. Now, I think this one's a little bit easier because it's less work, but
Is it actually?
it's easy because in the slopes you have to do 4 different slopes, right? Here you can only have to do like 2 sets of math instead of 4, but that's okay. So if a diagonal is going to bisect itself, so I'll sketch in the diagonal here. You don't have to. So there's diagonal BD and diagonal AC. What should be true about this point? It should be the midpoint of both diagonals, right? Shouldn't it be the point that's at the middle? So the midpoint. So how do we find midpoint? Not distance formula, not there yet. That's the one that's method 3, the one I don't prefer.
Measure the line and then cut it out.
So capital M. Remember, midpoint was you add your x's, divide by 2, add your y's, divide by 2.
That's the equation. I don't know.
So if I wanted to find the midpoint of diagonal BD, what are the x coordinates of B and D? 1 and 7. And then my y coordinates are 3 and 1. So that would simplify to 4, 2. Are we in agreement with that? So now I'm going to do the same thing for the second diagonal. So do it for AC. So the midpoint of AC would be 2 and 6, cut in half, which is 4.
4, 2.
And then -1, 5, which is 4 divided by 2 is 2. So are your midpoints the same?
Yeah.
So because my midpoints are the same for both diagonals, I could just write something like if diagonals bisect, then parallelogram. Which is easier? Finding 2 midpoints or finding 4 slopes?
4 slopes.
Okay.
I mean,
I mean, it depends if you can do it in your head fast, and it's easy numbers.
Right. Okay. Method 3, let's show congruency. So this is where the distance formula is going to come into play. Maybe people love the distance formula. And now that we know the Pythagorean theorem, we can technically just use the Pythagorean theorem instead of the distance formula to find the lengths of those sides. You want to do Pythagorean theorem instead? All right, so method 3, we're going to show opposite sides congruent. Yeah, so your distance formula, let's write it just so you guys have it. It's the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. That whole long thing. But now that we've completed chapter 7 and are proficient in it,
I'm not.
if I wanted to find the length of BA, does everybody see how if I drop perpendicular lines that right there, I just created a right triangle where the hypotenuse is BA? You see that right triangle right there? What's the length from this leg?
5, 4.
1, 2, 3, 4. This leg is 1, a squared plus b squared
C squared.
is equal to c squared.
So 16.
So AB
Is 17.
is going to be equal to whatever the square root of 4 squared plus 1 squared is. So 16 plus 1 is the square root of 17. I'll just leave it like that.
4.1.
Just leave it like that. If we do the same thing for CD, is that triangle going to have the same leg lengths?
Yeah.
It's still going to be 4 and 1. So really it's not too challenging because then I can just kind of repeat this and cheat and just say it's the same. Most likely you're probably not going to have a problem that it's not a parallelogram. So you can just kind of repeat it. So now let's do it for BC. What would be the leg lengths for BC of that triangle? Two and 5. So it's going to be the square root of 2 squared plus 5 squared. So what is that? 25 plus 4, so 29. And then I'm going to cheat and just do the same thing for AD because I'm going to assume it's the same. So, is it true that AB is congruent to CD? Is AB congruent to CD? Yes. Is BC congruent to AD? Yes. So give me an if-then statement. If what? If opposite sides congruent, then parallelogram. You choose slopes, midpoints, or distance formula.
Distance formula.
Shut up, Owen.
Okay. If you are using the slopes, you do need to make sure that you say something like AB parallel to CD, BC parallel to AD. The midpoints, you don't really have to show anything in there, just other that they're the same points. For this method, you do need to show AB is congruent to CD, BC is congruent to AD. Okay? All right, flip on to the back. Let's see if we can identify all the theorems. Do we have enough information to say that this is a quadrilateral, yes or no?
Yes.
Yes, why?
Alternate.
Alternate into.
Opposite angles congruent.
Opposite angles are congruent. Good. So yes, opposite angles are congruent.
Yes. Same thing.
Yes. Opposite
This is a no.
angles congruent. All right, number 2.
There's only 2.
Do we have enough information?
You don't.
You don't estimate that 115.
Why not?
Actually.
Oh, wait.
Can we find it?
Does that be equal 360?
Yeah.
We know it has to be 360, so when I do the math, that does end up being 115.
Yeah.
So do we have it?
You also lost that out because,
Yeah. So yes, opposite angles are congruent. Sorry, my handwriting's getting worse as we go.
And then the next one's obviously yes.
And then this one, yes. Why? Opposite sides are parallel. And that was it, right?
Yeah.
Okay.
This is where I drop out. This is easy.
Alrighty. Had 2 proofs they were going to add. So let me go ahead and